everybody, my name is Palma London and I'm a graduate student at Caltech. I'll be presenting joint work with Shai Vardi at Purdue and with Adam Weirman, my advisor at Caltech. So I'll be talking about solving very high dimensional optimization problems where we want to solve the problem in a distributed setting. And as a motivating application, let's imagine that throughout the country, we have a network of data centers. And together they are involved in solving a optimization problem. However, at each location, we have stored a subset of the problem data. For example, you could imagine that Google or Facebook have different data centers throughout the country. They will store local information at these different places, and they want to do some large computation, which involves all of this data together. And so what we're going to present in this talk is a distributed algorithm. And one of the key bottlenecks in this setting is the communication complexity or the cost of sending messages between nodes in this network. And what we're going to present is a distributed algorithm that uses far fewer messages than existing distributed approaches typically require. So as a preview, we're going to compare our algorithm, which we call LOCO, with ADMM, which is a very popular dual decomposition algorithm, which can be employed in a consensus distributed setting. And we show that in terms of the relative error, we have very competitive relative error, which measures the solution quality. And we also use far fewer messages than algorithms like ADMM here. So the problem that I'm going to talk about here is a case where we're minimizing a sum of convex functions, where each function is dependent upon xj, where xj is a scalar component of the solution vector x, which is an Rn. This is subject to a set of linear constraints. And throughout the talk, I'll be talking about this A matrix, which is an m by n matrix. And we're going to be considering problems where this A matrix is really, really huge. And existing approaches typically may not scale when this A is very, very large. And we're also going to be considering cases where the A matrix is a very sparse matrix, and we'll get more into that later. So before I go into the details, let me give you a very general idea of the approach we're going to take. So we're going to start with this extremely large problem initially, which is an m by n, has an m by n matrix. Somehow we're going to figure out how to decompose this very large problem into a series of smaller subproblems defined on a much smaller matrix, each of them. And we're going to solve these smaller problems locally at various nodes in the network. So going back to the idea of a network, so we have this physical graph. At each node, we have an agent. Let's say I'm agent 1, and I exist at this red node here. My goal is to obtain a solution to my local variable x1. And at each location, each agent, again, has a subset of the data matrix A. So you could literally think of this as a subset of the rows of the constraint matrix A. So the approach we're going to take is we're going to define what we call local neighborhoods around each agent or each node. So let's say for node number 1 here, we might define a local neighborhood that looks like this. And what we're going to do is we're going to share information just between these nodes. And this is going to enable agent 1 to collect some information or some sub-portion of the A matrix and then define a local problem. And that local problem is going to be defined on a subset of the variables. So for example, here, it might depend on only these variables here that are sort of popped out here. And so in terms of the matrix, what we're essentially doing is we are kind of carving up a subset of both the rows and the columns of the A matrix. And we are having node 1 just look at this subportion of the matrix and solving a smaller problem defined only on this part. And before I proceed further, let me compare this sort of approach with existing methods. So there is an extremely large body of work on distributed algorithms. A large amount of them are dual decomposition methods. For example, ADMM is a dual decomposition method. Many of them are consensus-based algorithms. And so in a consensus-based algorithm, and if we go back to the last slide, each of the agents has a full set of all of the variables in the problem. So each agent will compute an estimate to the complete solution vector X in Rn. What we're doing here is we're kind of asking a different type of question where we say, you know what, there's applications where you have local agents. They only care about their local actions, what they have to do locally. And so maybe they only care about, I'm agent 1, I only care about solving for X1. How can we use that setting to our advantage so that we maybe don't have to pass as many messages as an algorithm that is operating in the consensus-based approach? So let me give you a high-level idea of the type of approach that we're going to have. So we propose an algorithm called LOCO. And essentially, if there exists an online algorithm that can solve the problem we've proposed, what we're going to do is we're going to kind of convert that local algorithm into a distributed algorithm. And our distributed algorithm will have the same approximation ratio or the same solution quality, that is the same guarantee on the solution quality as the online algorithm. And the number of messages that we use is going to be in the order of log n plus m. So now, before I proceed, I'm going to make a connection with a field in the theoretical computer science community, which is called local computation algorithms. And essentially, the idea here is you have a problem on a graph. You define local neighborhoods, as I described earlier, where you only share information amongst the nodes in the neighborhood. And so far, this kind of idea has been applied to problems on graphs. And for the first time here, we are extending these ideas to optimization problems. And we are using a result that says that if we have an online algorithm, we can convert it to a local algorithm, or basically what we're going to have here is a distributed algorithm. And I was just mentioning online algorithms, and to make sure we're all on the same page about what I mean when I say an online algorithm, here I'll be considering covering online algorithms. So that means that we are considering the case where the constraints arrive online. And so, for example, this might be the row of the first row of the A matrix at time 1. We see this row. We update some of the some of the primal variables based on the support structure of the constraint. And we keep doing this, and so forth. We update the primal variables and the dual variables. And I will also, here we'll be talking about the competitive ratio setting for online algorithms rather than the regret setting for online algorithms. So now let me give you a very high-level idea of the full algorithm. So as I described before, for each node in the network, we define a local neighborhood around it, and we pass information between nodes in the network. And then the second step is that after we've passed information, we stop doing any kind of communication, and each node will solve its local smaller problem using the online algorithm. And you might be wondering, okay, how are all these solutions going to be kind of consistent with each other? And essentially, we are going to enable them to be consistent because they're all using the same online algorithm. and they're all considering the same constraints, which might overlap in the same order. And I'm going to get more into how that works. So let's walk through a very concrete example. So let's say I'm agent number 1. This is the full A matrix in the problem. I would like to solve for x1. The first thing that happens is that we define a random ordering on the constraint. So this is basically a permutation on M. And the reason for doing this is that this is going to help us simulate the online arrival of constraints. And I want to emphasize again that we here are not solving an online problem, but we are kind of using the machinery of an online algorithm within the context of helping us define a new distributed algorithm. So let's say I'm x1. I'm agent 1, I want to solve for x1. To help us describe the algorithm, I'm going to introduce a hypergraph. So here, each node corresponds to a variable, primal variable. Each hyperedge corresponds to a constraint. And the algorithm will proceed as follows. So I'm agent 1. I start at the node corresponding to x1, and I select the constraints that are involved in, that have a non-zero coefficient corresponding to x1. And these green arrows are to help us remember the rankings or the ordering for each constraint. And what's going to happen is that we're going to kind of walk through this hypergraph, collecting edges as we go. And we're going to stop at some point. And the stopping criteria is that we're going to select a new edge, new hyperedge, if the ranking here, so the ranking here is 1, is less than at least one of the ranks of the previously traversed edges. So here 1 is less than 2. We're going to select this new edge. Now we have an opportunity to select this next edge, but we're not going to take it because 3 is larger than 1. So we're not going to take that one. And so this essentially corresponds to this sub-portion of the matrix. And we've essentially selected a subset of the primal variables and a subset of the dual variables. And we can define this local problem for x1. Or here I wrote just a generic local problem for xk. Now, you might be asking again, how is this working? What's going on with the online algorithm? One of the ways to kind of understand this intuitively, just for this talk, is to say, what if I were to run the online algorithm on the entire problem? How is the variable x1 being updated? So the constraints will come online, and during some iterations, x1 will be updated. So here, during the second and the third iteration, x1 will be updated. Now, there'll be some iterations that do not affect the updates just to variable x1. And at some point in time, we'll be able to ignore constraints, the arrival of constraints that simply do not affect updates to x1. What we're doing is we're trying to pull apart the iterations of the online algorithm, if run on the original problem, that affect x1 and the ones that don't affect x1. And we're saying that agent 1, who only wants a solution for x1, can decide to kind of ignore some of the constraints that would not affect the value of x1. And that's the core of what we're doing in this algorithm. We're trying to tease apart which constraints affect which variables. Now, let me give you a concrete idea about what I mean when I talk about messages. So before I was talking about messages being sent between nodes. And as I was describing before, we send information between this local neighborhood in the physical graph. And I want to emphasize that this is in the physical graph, which corresponds to the geography of where the data centers are. It doesn't correspond to anything to do with the hypergraph. Okay. And a message essentially is a question that is asked from one agent to another, which says, do you have any locally stored constraints that involve a non-zero coefficient that corresponds to my local variable? And if so, please send me that constraint. And again, this is a very sparse matrix, and so it's essentially sending a few coefficients with their indexing information. And I want to emphasize that this message passing is being done in the first phase of the algorithm when the local problems are formed. And then in the second phase, where the online algorithm is used to solve the smaller problems, there's no more communication at that point. And this sort of setup is very different from many distributed algorithms where there's messages like constantly being passed between nodes. Okay, so here let me write down the statements more formally. As I said before, we will achieve the same approximation ratio. Here I call it h of n and m. And we will do this using an order log n plus m messages. And I want to highlight kind of the core argument that we have to make, which is that we have to bound the size of the largest possible set of constraints that might be involved in one of the local problems. And this depends on the degree of the hypergraph and also the degree of the physical graph. And essentially, this works well for very sparse matrices. And as the matrix becomes less sparse, it's harder to limit the size of these constraints, of the subset of constraints selected. Now let me show you some experimental results. So here we've compared our local algorithm with ADMM. Here we have two different lines for ADMM, which correspond to different stopping criteria for ADMM. And we see that even when ADMM has a pretty relaxed stopping criteria, we are still able to use far fewer messages than ADMM. And here on the horizontal axis, we are varying the sparsity of the matrix and as well as the number of variables in the problem. Here, this is the graph that I showed earlier on. Here we have ADMM for different stopping criteria, different stopping tolerances. And our algorithm has a very competitive relative error, and the number of messages is far fewer. And I want to emphasize this about the relative error, which is that our results are in terms of approximation ratio, but we basically can make that very, very small. And so it's truly is competitive with results that have different types of quality of solution characteristics. Okay. This is a result on SVM problem applied to a very standard router's text categorization problem. And we see that the training and test error is very comparable for local and ADMM. The number of messages is an order of magnitude less. So in conclusion, I presented a distributed algorithm for solving very high dimensional optimization problems. We are targeting a situation where we're really trying to send as minimal information as possible between the different nodes. We only send really very small portions of the constraint matrix between the nodes. And we also send very few messages. However, we're able to get a very high quality solution, and the number of messages is far fewer compared to existing distributed approaches. So thank you. Thanks for listening.